Hello, everybody. Thank you for joining our Cable Tech webinar series. Today, we're going to be talking a little bit about the evolution of OSC, the OSP plant. And Carl Goldsmith will be our presenter today. Carl, the floor is yours.
Thank you very much, Hilde, and welcome everybody. Maybe I'll clarify a little bit. We're not going to talk today about the advances in engineering in the plant itself, but we are going to talk about advances in meters, and in particular, a new meter that we're introducing this month from VeEX, the CX380C. So as we go through this piece, folks, we have about 30 minutes, which is not an awful lot of time. If anybody has any questions at all, feel free to use the chat room to ask any questions. We have some folks monitoring that, and we'll try and get those questions answered if they do appear. So if we look at the HFC plant itself and why we decided to reintroduce a version of our 380 test set, let's just take a look at where we're at today. The subtitle of this is "The HFC Plant May Never Die," and I think that's probably true. It'll be a awfully long time, no matter how fiber deep we go. Today, DOCSIS 3.1 deployments are in full gear. We're currently working up to 1.2 gig spectrum to deliver about 5 gigs to end subscribers. And we either have a low, mid, or high split, that is 42, 80, or 204 in the upstream that was capable of delivering 1 to 2 gigabits in the upstream. DOCSIS 4.0 specifications have just been released, and a couple of things worth noting. Extended spectrum DOCSIS, or ESD, will extend that downstream spectrum to 1.8 gig with the intent of delivering up to 10 gigabits to the end the subscriber. And full duplex mode will also present some changes. Specifically, the upstream split will move all the way up to 684 megabits, which will enable up to 6 gigabits in the upstream, yielding competitive symmetrical type products for business services. All of this stuff obviously will require Node plus 0 and remote PHY architecture. There are future plans that go beyond what we're talking about here, which bring that spectrum beyond 1.8 and out to 3 gigahertz. And the HFC plant continues to prove its robustness and resiliency. Experts predict there's another 30 years of useful life for the HFC plant. So with that in mind, it makes sense for us to take a look at meters that will work in yesterday's plant, in today's plant, and in tomorrow's plant. And so the CX380C at a high level, this is a meter that we designed with the intent of being targeted toward an advanced plant maintenance tech, but one that is much more budget friendly than they may have been in the past. For those that have used some of our test sets in the past, you'll notice that the form factor is exactly the same as its older brother, the 380S. This one uses the exact same form factor, but we've made some significant changes. The interesting thing about this one, and this doesn't happen often, but we've been able to make it more powerful and do more, yet reduce cost. And that was the challenge that we put to the engineers, and I think we've really delivered. So on a high view, we've got a spectrum analyzer that is faster and deeper. So we've got about a 50 to 60 dB noise floor on our spectrum analyzer. It is a true spectrum analyzer, not just using something like full band capture and some fancy digital processing, but a true sweeping spectrum analyzer that has a 1.8 gigahertz range. We support sweep in this meter with that will support in the downstream up to 1.8 gigahertz, and in the upstream will support up to 204 or a high split range for the upstream. This includes an extensive DOCSIS 3.1 OFDM analyzer. This is the same analyzer found in the other VeEX products, so nothing has been taken out, but it's just as powerful, and we'll kind of dig into that a little bit as well. We've introduced something that we've introduced to our fulfillment meter into this one. It's called VCheck, which sort of becomes the gateway into testing with this meter. It's a fast level MER, BER, OFDM scan using multiple test engines, and is capable of not only doing fast scans of our channel lineups, but also being able to discover those lineups, saving channel plans and things along those lines. We support speed testing. That's the UCLA compatible speed testing for both the RF and the Ethernet interfaces, meaning that we can test up to 4 gig on the RF and we can test up to 1 gig on the 1000 base T interface. Also support RFC 6349 base testing with our VPerf TCP layer 4 test. And interesting enough, just to make this a full, well-rounded test set in a truly HFC, that is a hybrid fiber coax environment, we've added a broadband power meter built into the meter itself, and we've added a TDR as well as a DMM for looking at AC, DC, and voltage and resistance. We've got a single RF port for both the cable modem and the signal level meter, which is a little different from the 380, which had 2 separate ports. And we've got an enhanced top design and fan covers for better protection against water intrusion. So you can kind of take a look at a blow up of the top screen. From the left, you see that we have 1 of 2 USB ports. It's followed with the 10100, 1000 base T interface for doing testing through CPE, such as a cable modem. The auxiliary port is used for our KLENS 3010H plus sweep testing. You've got your RF in right center mass of this box, which allows us to do both the cable modem measurements as well as the spectrum and signal level measurements type measurements. And then off to the right, the new interface is the TDR over here in the middle. You've got the optical power meter right here. It's a universal port, happens to be showing a Frank Charlie interface, but you can equip that how you'd like. And then we've got the DMM on the far right. So a well-rounded test set that sort of improves on what we had and really tries to address where customers are going and what they need in the field today. So just taking a walk around the meter itself, I indicated to you earlier that VeEX is sort of, not only is it a new feature, but it's sort of the gateway into doing testing. It's kind of where you go first. So this will allow me to discover and validate the channel lineup and then continue on to other testing. And what I mean by that is, if you look at the first screen, we will provide you a discovered channel table. We can also apply a channel table. That means that we can either use a channel table that we've defined, or we can use the discover mode where it will tell us what is there. So you have the best of both worlds. In certain cases, not using a channel table and discovering what's there has its downsides, because if a channel that you expect to be there is not there, then you won't know it's not there. So we have both modes. In either mode, it will color code the screen. So you can see the way to read this is I've got the full spectrum sitting on the top, and you'll notice that there are grays, greens, yellows, blacks, magenta, light blue, and dark blue. And the way to read that is that we've got a combined measurement there of both level and MER. So your top greens happen to be the MER readings for each channel or QAM. And the gray, light blue, and everything below the green is the MER. So I go from my left to right. The grays are my video QAMs. The blacks are my analogs. In this case, this happens to be my channel lineup, and it winds up being a couple of pilots. So we see a black one here and here, which are my analog pilots. Moving to the right, the light blue is the OFDM, with the purple or violet right in the middle there being the PLC. And then you'll see yellows and blues on the far end. Those happen to be my DOCSIS carriers, and we differentiate primary and secondary DOCSIS by blue and yellow. If I move the cursor, which is now sitting right in the middle of that OFDM block, I will see a blow up of 10 6 meg channels down below. In the case of the OFDM, those represent just that, 6 megahertz of OFDM, but it doesn't mean a QAM channel. But if I go over to the left or to the right into my DOCSIS and video QAMs, then I will see the actual video QAMs themselves. Channel numbers will be identified on the right. The frequencies, the levels, and the modulation would be on the right as well. So you can see that this is an OFDM modulation. It's got a frequency, in this case, of 645. That represents channel 94 on a normal lineup. And then I see a level that's 10.5. If I want to move to the right, as I see on the screen off here to the right, if I move it into that area over here, you can see that now I'm looking at the blues and the yellows. And again, the MER is on top, and the level is on bottom. So we can see this is sitting right now on channel 134. That is a primary DOCSIS because it's blue. If I put it on the yellow, it's a secondary DOCSIS. If I want to see the modulation, the channel, the frequency, any of those things are resident for me right here. If I hit the page up and page down, the page down was pushed, and you can see the table shows up over here. If I push table, I then see the complete table. So I have it in a tabular format with the channel, the frequency, the modulation, the level, the MER pre and post, and then the adjacent channel measurement. Now, if I want to save this as a table, all I simply need to do is hit Save Table, and this will save the table for me for future reference. And then I can use that when I go to another channel. I'm going to go back just for a minute. If I want to look at the detailed channel information for any of these here, I indicated that this sort of becomes my gateway. If I want to go to the cable modem, all I've got to do is line myself up on the cable modem, one of the DOCSIS cable modems, hit connect cable modem, and I will launch the cable modem. If I want to do the OFDM, all I've got to do is lock onto the PLC. So just move this slightly over here, hit the purple one, and that will bring me to OFDM. If I want to look at the single channel measurements, not just the scan, but I want to see a continuous measurement of the channels, I just hit channel detail. So truly the gateway into pretty much anything you need to do. You can see your faulty channels, you can identify which ones are up, which ones are down, which ones are good, which ones are bad, whether I've got a suck out or what it looks like. As I cruise down, if I want to look at the cable modem itself, I like to say that we've got a true DOCSIS 3.1 cable modem. It is both 32 by 8 DOCSIS 3.0, as well as a full 3.1 supporting up to 2 OFDMs in the downstream and 2 OFDM-As in the upstream. This is showing it ranged up and connected. The primary frequency in this case was 855. And if you look on the right, the information that's really relevant for this particular connection is the DOCSIS mode is identified, i.e. did I link up 3.1 or did I link up 3.0? A critical piece of information given the fact that we're working in a bonded environment. If I don't lock 3.1 because there's a problem with my OFDM, I will normally lock 3.0. If I'm not paying attention to how it locks up, then I might get myself in trouble. Bonding of the SE QAMs is identified, so I'm running 32 by 5, so I've got 5 channels bonded in the upstream and 32 channels in the downstream. It's telling me that the one downstream that I'm using, my one OFDM, the PLC is at 744, and the center frequency of my one OFDM-A is 60.02 megahertz. If I want to then look at the rest of this, all I simply do is tap on the various tabs. So if I tap graphs, I will get a graphical representation of what my link up looks like. And you can see the downstream is on the left where I see an OFDM followed by all my DOCSIS carrier, my SE QAMs. And then on the right, I see my one OFDM-A along with my other UCDs. If I tap on link because I want to get a little bit more information about what's going on behind the scenes, now I can look at all 31 of my SE QAMs. I can look at my OFDM, which is right over here at 32, and you can see that there are 6 pages. I happen to be on page 4 of 6, and if I want to now go and look at my upstream UCDs, I can just kind of cruise to the right. I'm now on page 5 of 6. And not only do I look at the UCDs, but as I tap on each UCD, I get the adaptive equalizer and the frequency response, peak to valley identified right here, which is of course my ICFR. So very, very quickly, I get that information. And if I want to look at whatever is available for the OFDM-A, I simply look at the next page and it will show me the center frequency, the modulation, the level, and of course the symbol rate. So if I now want to look at the OFDM itself, just tap on the OFDM, and now I'm able to look at the OFDM. I look at the both average, max, and min on my levels over here on the left. I reiterate for you what your PLC frequency is. I identify it as 192 megahertz wide in this case, so the OFDM bandwidth is identified. And then the subcarriers that are being used, 50 or 25 kilohertz, are identified in how many active subcarriers I have, which is 3,800 in this case. Notice that I give, like a lot of different test sets do, I give you the average MER, I give you the standard deviation, and then I can allow you to look at some sort of variable of the worst percentile. In this case, I'm looking at the lower 2%, but I can vary that to whatever I want. Notice also that I identify all of the profiles and channels that are locked. So everything with a green lock indicates that it's been locked. Anything that's red means it's not locked. Anything that has a modulation populated in this column here means that it should be locked and it's provisioned. So the fact that profile E isn't locked is perfectly okay because that one hasn't been provisioned. But we do see that they're all provisioned. What we don't know is which ones are being used. So we have this little button here that allows me to switch from just looking at the MERs and the correctables and uncorrectables as rates, because this doesn't tell me what's happening now. I can look at, by hitting details, I can actually see the counts. So now I can see the total code word counts, the correctables and the uncorrectables, but most importantly, we will be able to see which ones are increasing. The ones that are increasing is the profile that's actually being used. So if we are looking at this screen right now and we notice that the profile A, 256, is humming along and these are stationary and not incrementing, that tells me that yes, the OFDM is up. Yes, I'm locked with all the profiles, but no, it's not really good because the cable modem CMTS have decided that they can only use profile A. So a very valuable tool as far as looking at how it's working, not just if it's working. But what if it's not working well, and you notice a profile D, C, and B are not being used, and you notice that you have an MER standard deviation that exceeds a certain level? How can I look at something beyond that? All I've got to do at that point is hit the subcarrier scan, and now I will be able to show to you all 3,800 individual subcarriers. I will identify the levels, the MER for each one of those 50 kilohertz subcarriers, the noise that exists underneath each one of those subcarriers, and then of course the comparison of MER and noise so that I can figure out if my low MERs are due to a suck out or level change, or are they due to increased noise. I think I have another screenshot further into the presentation which will go into a little bit more detail there. Once I've done that and I've connected and I'm ready to go, the next thing I want to do is I want to validate that I'm getting the appropriate speed. So we've got the ability to test RF, meaning from the cable modem. So you can see in the configuration that we have here where we have an OFDM with 192 megahertz wide running profiles up to 4K and 31 downstreams, we're capable of seeing almost 4 gig of traffic, and you're seeing 3.5 gig in the downstream, and we're seeing almost 300 meg in the upstream. Now, if I were to test through a CPE on this same one, we wouldn't expect to see 4 gig because we only have one single 1000 base T. And of course, what we're seeing is something closer to 1 gig minus the overhead. But notice it's capable of measuring 1 gig in both the upstream and the downstream. That is, it's able to do that symmetrically if it's symmetrically provisioned. So again, UCLA, compatible speed test, exactly the way your customers are testing these speeds and feeds that you're delivering to them, either through the RF interface or through the Ethernet interface. I said that I would show you a little bit more about the OFDMs, and these screenshots kind of help you see that. So this is truly a best in class from a standpoint of OFDM measurements. There isn't another test set out there that gives you the same level of detail. And as you can see at the bottom, we're actually got a patent pending on our subcarrier scan. So most everybody can give you something that looks a little bit like this, although I don't know of anybody who does it quite as visually and uncluttered. It's very simple for me to see how I'm working and when I'm working. And the ability for me to switch from rates to counts is invaluable if I'm trying to figure out what is actually working. Not only am I locking up, but is it working well? The ability for us to move to the subcarrier scan is sort of identified here. This is a picture of the MER scan. The way to read this is the entire 192 megahertz down below. And I can move that little cursor that's sitting right here, left or right, in 6 megahertz hops. Once I've settled it into a place, then what will show above is a blow up of that 6 megahertz channel, which means that I will see the 120 50 kilohertz subcarriers above that. Green will always be identified as my continuous pilots, and the blue ones here are my data carrying subcarriers. As I move the cursor to any one of those, I will see the MER on each 50 kilohertz or 25 if I'm using 25 kilohertz subcarrier. So in this case, I'm looking at 739.950, and it's got an MER of 3.7. Now, why is the MER dip so bad here? If I just go to the noise floor and look at it, this is what the noise floor looks like. And this is what the noise floor looks like overlaid or underlaid, if you will, with the MER right above it. And notice that where the noise increases, the MER goes down. So we can see that the culprit in this case is probably something we introduced ourselves for demonstration. It looks like it's a continuous wave signal sitting right here, which we wouldn't see on the spectrum, but we can see very, very clearly right underneath the OFDM. So unparalleled ability and visibility into what's going on underneath that carrier when it's not running. Something also that I want to highlight for you is notice that I've got two icons sitting up here on the top. The icon to the right is the cable modem. The green on this one will indicate that the cable modem is locked. The fact that it's not locked is an indicator that I am locked to an OFDM, but I am not locked as a cable modem. And this is a very critical piece that you need to look for in any test set, particularly a plant meter who is going to be trying to look and find a problem within the plant. The ability for me to lock to the OFDM without locking my cable modem not only saves time, because I can do it in seconds versus minutes, but it also means that if I can't lock to the cable modem 3.1, i.e. the OFDM is that bad, I can still check the OFDM and figure out why it's not working. So the ability to look at the OFDM both within the cable modem, again, let's go back up and look at our screenshot from here. This is an example of where the cable modem is indeed locked up. I'm on the OFDM tab and I'm looking at the subcarrier scan within the OFDM or looking at the OFDM information right behind it. Okay, so that's a situation where we're looking at it when it's locked. And if this didn't lock 3.0, there'd be nothing in this tab. Or pardon me, if it didn't lock 3.1. And that's where the ability to do this without locking becomes critical. So we also have added the same kind of advanced features that we have in the 380S. That is, we have the ability to obviously do a single channel measurement, so I can look at the constellation, I can look at levels, MERs, pre's and post, but I can also go ahead and hit something like impairment and look at the detailed information. Now I'm looking at the symbol rate area, the frequency error rate, the frequency response, the group delay, and if I tap on the graph, I'll be able to see my adaptive equalizer, the group delay, and the frequency response very, very visually. So the ability for me to drill down on each one of those QAMs become paramount. But what if I can't lock to the QAM? So I showed you how I can look very, very detailed, like underneath the carrier when it becomes an OFDM. But when we have a QAM, which is a little bit different, we have that same need. So here's an example where my QAM, I'm sitting on channel 87 and my QAM is not locking. So you see it's locking. I can see a level, but that's all I've got. So I go to my spectrum analysis and I look at that QAM and it sure looks good. It kind of looks a little bit funky right here with a little bit of hump, but there doesn't seem to be anything really wrong with my haystack. And so I go to the iQAM capability, which gives us the ability to sort of take the QAM signal away and look at what's underneath. And we see that indeed we've got the existence of a CW sitting underneath that haystack. So we have the ability to not only look under the OFDM, but we have the ability to look under the QAM as well, all in a single meter. One of the most exciting things about this test set is the spectrum analyzer. The 380S, and for those that have used that in the past, will probably recognize one of the best spectrum analyzers outside of what we see in the head end, such as the AT2500. So a meter out in the field doesn't get much better than what we had in the 380S. Well, what we've done with this one is we've increased the frequency range, so we bring it all the way from 1 gig all the way to 1.8 gig, making it ready for DOCSIS 4.0 type qualifications. But we've also made it faster and we've made it more powerful, meaning that it can look deeper into the noise floor and it can scan faster so that it can do things like looking at persistence, which is what you see on the left-hand side, where I'm looking underneath a intermittent QAM such as my UCD or an OFDMA, and we've made it a lot easier. So instead of making a tech have to figure out how to use resolution bandwidth and VBW and all that fun stuff, we've kind of made it a little easier. And all you've got to do is select whether I'm looking at a digital channel, whether I'm looking at an analog, or whether I'm looking at a bursty event. Upstream would be bursty. Analog would be clearly if I have an analog system. And if I've got QAMs and OFDM, then I've got a digital system and I put it in digital mode. Then all I need to do is select resolution, high, medium, or low, which allows me to just add more and more data points. And then what I'm left with is a screenshot that is incredibly easy to read, incredibly easy to use, and just works in a way that makes it so much easier to be chasing noise in the plant when I indeed have problems. So again, one of the key features of the box, something that it hasn't changed. You got the same functionality and features as our original spectrum analyzer. We just made it faster, better, and stronger. And then what we've done is we've added the ability to look at the drop if I need to. So if I'm sitting at the end and I'm actually sitting there looking at a customer drop, I have the ability to look at that TDR, measure distance default, the way I typically do with the time domain reflectometer, just not making you carry another test set. And with my digital multimeter, I have the ability to look at DC volts, AC volts, and ohms. So we can identify proper power input for amplifiers. Think about what we do when we're checking a node. The first thing that I do when I come up to an amp or to a node is I'm going to look and see if I have RF. If I don't have RF in, I start looking behind that. If I have RF in, but I still have a problem, I want to look and see if I have AC power. So I look to see if I have 90 or 60 volts coming in. If I have 90 or 60 volts coming in, then I want to see where once it's inverted to DC, do I have DC voltage? If I don't have AC, I don't have DC, or I don't have, well, in either one of those cases, it indicates that I've got a bad amp or a bad node. So the ability for me to dissect that quickly with a single meter becomes very, very powerful. And likewise, if I'm at that node and I'm going back fiber to the head end, the ability to measure that power right there in the same unit simply by tapping that icon makes things much easier as well. This is a broadband power meter that has calibration for 850, 1310, 1550, 1650. So all the common lambdas you'll be using, it can be calibrated for as well. We've also got the ability to sweep for 3.1 and beyond. So we've got the in-service sweep that we've also been able to make significantly faster due to our spectrum analyzer and the spectrum board we're using. Very, very simple to use. Simply select the in-service sweep, select your channel table down here, measure your response, which is what we see here. We save that as a reference. We then go ahead and measure live at the next spot. We see that over here. We then load the reference, we create a difference, and we see hopefully what you see here. So this was done obviously in my home at the same spot, so you're not going to see much of a difference, but in a real environment where I'm on a live plant, you may see some deviation here, and that's when the balancing begins. But very, very simple, very, very quick as far as my in-service sweep is concerned. And of course, that will use all of my QAMs as well as my OFDM as its reference material. If I want to use the 3010H Plus as my transmitter and receiver in the head end, now I have the ability to not only test in today's environment of 860 and maybe up to 1 gig, but I can test all the way up to 1.8, which means I can begin qualifying some of that plant in preparation for DOCSIS 4.0 and ESD. I also have the ability on the upstream to test not only 42, but my mid split at 80 and my high split at 200. This is fully integrated to our vision system so that it's centrally controlled, so all the channel tables and sweep profiles can be downloaded and then distributed to the meters remotely. And obviously works with the 380C, works with our older 380S, and also works with the legacy CM3800s. The sweep tables, I think everybody here has probably seen how these how they're interconnected. So I'm going to spend time here, but I will spend just a brief moment talking about what we can do, because one of the things that we do is in our forward sweep is not only can we sweep in between, we can insert points in between our SE QAMs, and we use about 451 sweep tones that are looked at once a second. But we can also sweep through the OFDM. So what we do is kind of creative. We use the continuous pilots that we identify in the meter. So we can use those as our sweep points, so that when you look at a sweep sweep response, this is what you'll see. So this is my SE QAMs over here on the left. This is an OFDM coming in here, and then this is the rest of the network as I get down below. Looks like I'm going out to 1 gig, so it's kind of falling off. So why do I have this big haystack here? That's being measured with the OFDM, and it's using my continuous pilots. But if you go back to my diagram, you will, if I can get there, you will see, pardon me, you will see that the continuous pilots ride about 6 dB higher than the normal QAMs or OFDM. My sweep points will run about 10 dB below the QAMs themselves. So there's about a 16 dB delta between my sweep points and my continuous pilots, which is why you see this thing still raised up about 16 dB. But as I store this as my reference value and then go down the plant and begin to measure different ones, when I reload it as my reference, what you wind up with is that same flat line, because I'll still see the OFDM exactly like I will all the way down the line. So again, the ability to do in-service sweep if I desire, and the ability to do out-of-service sweep, being able to inject those sweep points in between the SE QAMs without interfering, as well as using the OFDM or OFDM channels as a reference point to fill out and fully balance your plant. Again, keep in mind that we're using typically 196 megahertz OFDM in the downstream today. However, that can be up to 192 megahertz wide, and we can have several of those. So as the OFDMs, which we can't insert into the middle of those because we can't insert in between 50 kilobit subcarriers, we need the ability to still be able to sweep using those OFDMs. So I think I've just about hit the end of my 30 minutes. I don't know if there's any questions, and I'll let you guys ask if there are. If there aren't, you guys are welcome to come see us at our virtual booth. We can show you virtual live demos of this equipment as well as others that we have. The link here will take you to our virtual booth, and we'd be more than happy to chat with you there as well. So that concludes my introduction of the 380C. Is there any questions from the panel?
So, Carl, it looks like you've put together a great solution for the expanding HFC plant, and it looks like you're going to be able to really help people address the new requirements as the extended plant needs to be swept, and that you've definitely come up with a good, powerful solution for the folks out there that are going to be dealing with this going forward.
Yeah, I think we have, Neil, and I appreciate the quick summary. And the amazing thing about what we've done here, and it doesn't happen often, but we've been able to do this at a price point that's lower than where we were before. So we've gotten better, and we've gotten lower cost, which is a real bonus.
Great, great. Always good to hear about cost-effective innovation from VeEX. Thanks so much for a great presentation.
All right, guys, thank you for coming.